In this lesson, we'll be extending our discussion on how to extract information from the periodic table. Just as artwork in a museum is grouped by shared characteristics, elements are organized into families that share similar chemical properties. By the end of this lesson, you'll be able to look at an element's position on the periodic table and make meaningful predictions about how it behaves. So we've already seen that we can extract the number of valence electrons that an element is likely to have just by its position from the position on the periodic table. So this is just a reminder. So we go 1, 2, remember all these guys in the middle, and the transition metals have 2 valence electrons, and that's because the s orbitals that precede them are at a higher energy level. And then 3, 4, 5, 6, 7, and 8, except for helium, which only has 2 electrons in the first place. Now, the periodic table is also divided into metals and nonmetals. And one of the ways that you can figure out which one is which, if you're just looking at a kind of blank periodic table like this one, is to remember that aluminum is a metal, aluminum foil. Just think of how shiny it is. And so there is actually a stair step that goes between the elements. You start with aluminum, and then you just have to imagine I have a more modern periodic table here. And so all of the elements that are, almost all of the elements that are on one side of the periodic table are going to be metals, and the elements on the other side are going to be nonmetals. So let's look at the first category I have are metalloids. Now, metalloids are neither metals nor nonmetals, but they share characteristics with both. And if you notice, they're kind of sitting here on the stair step line. So if you just remember where the stair step is, you can also remember where the metalloids are. And just remember, aluminum is a metal. It's kind of a weird metal, but it is a metal. And then we got metals. That's what most of the periodic table is. Hydrogen is over here on the metal side, even though it is a nonmetal, because it shares properties with this first group. It has 1 valence electron, for example. Sometimes you might see periodic tables where they have hydrogen over here above fluorine, and that's because sometimes it can behave like this family of elements. Most of the time, though, it behaves mostly like the first group. All right, so let's talk about some general properties. So metals, the reason why we know aluminum is a metal is because it's reflective. And that's because we have delocalized electrons that are able to respond to the electric field component in the incident light and causes the light to be reflected from the surface. Metals are also good conductors of heat and electricity, again because of those delocalized electrons. They are usually solid. Mercury is the exception to this. Mercury's kind of freaky. It is the only metallic element that we have that is a liquid at room temperature. They are malleable. That means that they can be beaten or rolled into thin sheets. I just think of whacking something with a mallet, so malleable. And then they are ductile, which means they can be drawn out into wires. And then over on the nonmetal side, we have their characteristics. Now, nonmetals means it's kind of like the opposite of a metal. So if a metal is shiny, that means a nonmetal is dull. Nonmetals are poor conductors of heat and electricity, and they tend to be actually insulators. Nonmetals are usually gases, and then if they are solid, they're going to be brittle. Sulfur is a nonmetal. That is a solid, but you can crush solid sulfur in your hand, so it's very brittle. Metalloids, like I said, kind of sit in the middle, and so kind of got a Venn diagram of sorts. And so metalloids are going to share properties with both metals and nonmetals. Metalloids are shiny, but not as shiny as metals. They will conduct electricity under some circumstances, but not as well as metals do. Metalloids are also usually solid. Can't think of any gaseous versions of them. You can shape them into things, but they're a little bit more brittle than metals are. So metalloids, for the most part, act more like metals than they do nonmetals, but they do share in between. All right, so we have some named families on the periodic table, and the reason why they get these special names is just because they're all in a column, all in a group together, and they have shared properties. So just like we can look at this picture and say, all right, yellow skin, bad overbite, these are the Simpsons. We can also look at the different properties of the elements and say, oh, those are acting like alkali metals, for example. So looking at the periodic table, group 1 are the alkali metals. Like I said, hydrogen is not a metal, but it shares properties with the alkali metals. Alkali just means that if you put these into water, once they're done reacting, they will form a basic or an alkaline solution. Group 2 are the alkaline earth metals. So alkaline, in this case, again, means the same thing. You put them in water. They're not as reactive as alkali metals, so it's not quite as exciting. And they will eventually react with the water and form a basic solution. The earth part of it tells you that it likes to combine with oxygen. So we got things like beryllium oxide, magnesium oxide, calcium oxide. The earth just means they combine with oxygen. It's an old term. And then we got the halogens over here. I kind of tried to color code these things a little bit. So hal is, I think it's Latin. It's a word stem that means salt. So these are the salt formers. And if you notice, we have chloride in there. Remember, sodium chloride is table salt. And then we have the group 18, which are the noble gases. They used to be called the inert gases, and then somewhere like the late 70s or something like that, a researcher in California discovered that if you take xenon and some fluorine gas and a little bit of sunshine, it would react and form a white powder. And so it's like, okay, well, these gases are not noble, or are not inert. They actually do react, but they're noble. They don't like combining with the common elements. So they have formed compounds with xenon and krypton. They have not been able to form any compounds with argon, neon, or helium. They're just too small. I would assume that radon would also form compounds, but it's radioactive and nobody really wants to do any research with that. I should check on that to see if anybody's done it. All right, transition metals. These are the D block elements. And the reason why they're called that is because they're making the transition from the main group metals, which is what groups 1 and 2 are called, to the nonmetals. And then we have the inner transition metals because they are inserted into the transition metals. An older term for them is the rare earths. Again, it just means that they like to combine with oxygen. Now, because they're not columns, they're not groups, but they do share properties with lanthanum where they take off from. The first row in the inner transition metals are called lanthanides. They have properties that are very similar to lanthanum, element number 57. And then the row that takes off from actinium are the actinides because they share properties with actinium. All right, so we saw with the electron configurations that a really handy-dandy shortcut is to use a noble gas core. And the reason why we do that, why we use noble gases rather than anything else, is because noble gases have a very stable electron configuration. All of their energy levels, all of their shells are completely filled up, and so they don't want to react very easily. So helium is 1s2, neon ends with a 2p6, argon ends with 3p6. So if you're talking about anything that's not in group 18, they're going to be more reactive. And when elements react, they're trying to get to a noble gas electron configuration. So they're going to either gain electrons or they're going to lose electrons. And since they are no longer electrically neutral, they will be called an ion. There are two types of ions. So a cation is one with a positive charge. It is not cation, although I do hear that a lot. And an anion is an ion with a negative charge. Now, I've heard a lot of people just say different ways to remember this. One of them is that cation has that T in the middle, so it kind of looks like a positive sign. I had a friend who really liked cats, and so he would tell his students that, oh yeah, he likes cats, so he feels very positive about cations, whereas he does not like onions, and so he feels very negative about anions. So here we have lithium. Lithium is got a helium core, ends in 2s1. So if we get rid of that one electron, we will have an ion that has a noble gas electron configuration, isoelectronic with helium. So we do that. Now the thing about electrons, because they have that negative charge, it has the opposite effect. They're kind of backwards. So if you subtract an electron, you get a +1 charge. So the next one, beryllium, same idea. We're going to subtract 2, and we get a +2 charge. Boron, so if we subtract all 3 of these electrons, we'll get back to helium again. And so that would have a +3 charge. Now carbon, you could either subtract 4 or you could add 4. But the thing is that the carbon column, they don't really like forming ions anyway. They tend to form covalent compounds. So they share their electrons. So we're not going to do a positive or a minus assignment to it. So continuing with the trend, so nitrogen has 5 valence electrons. Now it requires less energy to add 3 electrons than it does to subtract 5, so that's what it does. Notice they go into the p orbitals because those still had some space, and you end up with an anion with a -3 charge. Oxygen, same idea, you end up with the -2 charge on the oxygen. Oh, and charges are also called oxidation numbers. And then fluorine, you only need 1 more electron, and then it's just like neon. And so that's what fluorine does. So some more trends to add to your favorite periodic table. We can get those oxidation numbers just by looking at location. And if you are adding this to your periodic table, make sure you put the pluses and the minuses on here, because if you don't have them on the plus, especially on there, it's going to look like a valence electron. So group 1, they all have a +1 charge when they're ions. Group 2, they all have a +2 charge when they are ions. The transition metals, because they have all those d orbitals and those electrons can hop around and do all kinds of crazy things, they can have oxidation numbers that go anywhere from +1 to +8. And we will see shortly on how to tell what the oxidation number is. There are some exceptions because, there's always going to be exceptions. Silver is always going to be +1. It actually does have a +2 oxidation state, but it's very unstable. So for simplicity's sake, we're going to say it only has a +1 charge. Whereas copper can be +1 or +2, and gold can be +1 or +3. So we're just going to remember silver is always +1. And then zinc and cadmium are always +2. And there is no variation there. They are always +2. Mercury, kind of freaky all over the place. It can form a dimer. It can be +1. It can be +2. So we're going to use this second way of designating it for mercury. All right, back to the main group. We have group 13. They're +3. Then we have our column carbon. So the nonmetals, they don't really form ions. Down here in the metals always form positive ions. They always form cations. And we will come back to lead and tin because they're kind of special. So we're just going to have this 4 kind of in parentheses. It's kind of 4-ish. And just because it helps with the trend. So we counted up 1, 2, 3, 4, and now we're going to count back down, but negative. So the nitrogen column are going to be -3, oxygen -2, and the halogens will be -1. And then the noble gases, they don't form ions, so they would be a 0 if you want to add a 0 for completeness sake. All right, the last bit that we're going to talk about in this lesson is the magnetic properties of the elements that are determined by how many unpaired electrons they have. So if you have any unpaired electrons present, it will be paramagnetic, which means that it does respond to a magnetic field. Typically they have an instrument, and with a magnetic field generated inside, and if your sample is paramagnetic, it kind of gets sucked into that instrument. So here we have iron plus 2, so it's missing its 2 4s electrons, but it still has some unpaired electrons in the 3d orbitals, so that means it is paramagnetic because it has unpaired electrons. Atoms or ions in which all of the electrons are paired, so you have for every up you have, you also have a down, would be, it's diamagnetic. It does not respond to a magnetic field. So we have zinc, which is 4s2 3d10. So you can see they're all paired up, so it will not respond to a magnetic field. If you had zinc plus 2, those 2 electrons come out of the 4s orbital because that's the highest energy level. Remember, we just look at those the principal quantum number, the big number, for the energy level. And so that one would be empty if you had a zinc plus 2. But the 3Ds are all still paired up, so you would not have any unpaired electrons. So both zinc and zinc plus 2 are diamagnetic. All right, so wrap up for this lesson. So elements in the same group, which is also called a family, share similar chemical properties. And this is due to the fact that they have the same valence electrons, which then contributes to very similar oxidation numbers and reactivity. We can use the location on the periodic table to get the common oxidation numbers. Like I said, there are exceptions, not just in the transition metals, but when you get down towards the bottom of the periodic table, the electrons can start rearranging themselves quite a bit, and you get a lot more exceptions. And then we can identify whether we have a metal, a nonmetal, or a metalloid based on where they are located on the periodic table. And being able to make that designation tells us what kind of reactions that they're likely to participate in. We have clear trends across the families as far as reactivity goes. With alkali metals, for example, as you go from top to bottom, they get more and more reactive, but the halogens go the other way. If you get closer and closer to fluorine, which is at the top, they get more and more reactive. And that's actually what the next lesson is on. So an element's location tells you how it's likely to behave, and just tells you that the periodic table is a map of patterns. It's not just a list of elements. So there's a reason why the periodic table has that really weird asymmetric shape to it. All right, so that's it for our lesson on periodic families. Thanks for listening.